For this problem, what we're going to do is look at the relationship between Ka and Kb. Now, Ka times Kb is equal to Kw, and Kw is 10 to the minus 14th. We're going to start with a monoatomic. We'll do a monoatomic, and then we'll do a diatomic, and then a monoprotic and a diprotic, and then we will compare and see what happens. So pick a simple acid, and we'll use hydrogen cyanide. So when it dissociates, it's going to dissociate into H plus and Cn minus. So when we look at this, this is the acid form, and this is the conjugate base. The Ka associated with this is H plus cyanide minus the conjugate over HCN. Looks pretty simple so far. It's just a simple Ka. Now, in order to do the Kb, we need the base form, which means we'll start with the conjugate base. Now, this works exactly the same whether you're doing acid or base. With base, you start with conjugate acid. So then we regenerate HCN plus hydroxide. So this would be the conjugate base. So this is the acid. Okay? So we have a Kb. Kb is equal to the products HCN OH minus divided by Cn minus. So now we have our Ka and our Kb of our related species. This only works for related species. If they're not related, you can't do this. So Ka times Kb is equal to H plus, that's your Ka, cyanide, over HCN times HCN, which is the Kb, times hydroxide, Cn minus. Now, this is simply a mathematics problem, so we cancel what we can. And so for simplicity's sake, I'm going to cancel Cn minus with Cn minus. HCN cancels with HCN. So what we're left with is H plus times OH minus, which we know is Kw. So, and Kw, remember, is 10 to the minus 14th. Therefore, if we have a K value, we would just plug it in and solve it through to find the appropriate Kb.